We're going to continue discussing about how to find displacement from the area under a velocity versus time graph. Now, in class and in previous videos, we've talked about if an object was speeding up in a positive direction, we might have a graph that looks like this, and the velocity versus time graph would be directly proportional, right? Today, I'd like to consider a new concept. Instead of like the graph we just showed where the y-intercept was 0 and more importantly, the slope of the tangent line at time 0 was 0, what if our position versus time graph didn't start with a flat line, but it was already tilted upward and speeding up? How would that change the velocity versus time graph, and how might that affect how we would calculate displacement from that? So if the object already had a positive slope at time 0, looking at the tangent line there, that would mean at time 0, the velocity would not be 0, it would be some positive velocity, and from there, it would speed up. So taking a look at what we have here, the y-intercept of our graph, as always, would be telling us the velocity when time equals 0, which means this clock reading would be the clock reading of 0. That's the clock reading when time equals 0, right? So, what would this velocity up here be? Well, that would be our velocity final. And what would this clock reading here be? That would be our final clock reading. Now, one more thing I want to discuss before we take this too far is we know that the slope of this graph is the acceleration, and it describes the rate at which the velocity changes with respect to time. But what if I wanted change in velocity by itself? What would I have to do to both sides? Well, we have to get rid of the change in time. To do that, we have to multiply both sides by change in time. And therefore, we could say that acceleration times change in time is equal to the change in velocity. Now, previously we had said that the area under a velocity versus time graph would give us our displacement. Well, it's still the area of this shape, but that's kind of an unusual shape. But maybe if we broke it into simpler shapes, maybe if we broke this shape into a rectangle and separately broke it into a triangle, then to find the total area under the velocity versus time graph, we'd simply have to add the area of the blue rectangle and the red triangle together. I'm going to move on to another screen now, but you might want to pause the video at this time if you wanted to sketch this out for yourself. Please be aware that all the notes that we're about to take are posted to this assignment as well if you'd like to follow along, or if you want to write them as you go, that's fine too. So taking a look at the graph that we just built, we said that the total displacement would be equal to adding the area of the red triangle, and to that we'd want to add the area of the blue rectangle. Now, to find the total displacement, we know the area of a triangle is one half the height times the base, and we know the area of a rectangle is the height times the base. Now, just to keep things a little more focused right now, we're going to stay focused on what's going on with this triangle, and we're going to expand all of this, and then we'll come back and take care of the rectangle in just a moment. So, for this rectangle, we say that one half the height times the base. Well, how would you calculate the height of the triangle? Well, really, the height of the triangle is this and this, right? It's the final velocity minus the initial velocity. So we go final velocity final minus the velocity at time 0, or you could say initial velocity at that time, times time final minus time 0 or time initial. To simplify that, we could say it's one half the change in velocity times the change in time. Now, do you remember earlier we said down here that the change in velocity is equal to acceleration times time? Well, doesn't that mean that we could fill in acceleration times time here for the change in velocity. Let's do that at this time. So we've got 1/2. Instead of change in velocity, we're going to use acceleration times change in time. The same thing there, right? Times the change in time. Now, we've looked at a simplification of this sometime prior to now. Except 1/2 times the acceleration times change in time times change in time. We could combine those change in time, so now we have 1/2 the acceleration times change in time squared. Now, we're going to take a break at this time and say that the displacement can be calculated. We have 1/2 times the acceleration times the change in time squared. But remember, we have to add the area of the rectangle. So going through similar steps, we'd have to add the area of the rectangle, which the height of our rectangle is actually the starting velocity. And the base of our rectangle is time final minus time 0, or change in time final minus time initial, or time clock reading times 0, which we could then simplify that into the velocity at time 0 is equal to the change in time. And we're just going to leave it at that format for the rest of this. Initial velocity times change in time, initial velocity times change in time. So what this allows us to do, this equation we've just built, says we can find the displacement for an object that is accelerating and is moving at time 0. It has an initial velocity. Is there anything else we could do with this? Is there a way that we could change this delta t? Could we break it into individual positions? Well, how would you calculate change in position? Well, if you recall, we can do that by doing final position minus initial position, or the position at time 0. And then all the rest of this doesn't change except for we don't have a final clock reading and initial clock reading. At this point, we're going to end up having to go to 1/2 acceleration So now that we've broken this into a final position and initial position, how do we get final position by itself over here? Well, we'd have to add the starting position to both sides. Add the position at time 0 to both sides. So that's going to cancel over there, and that's going to move it to the other side. When we do this, now we're really talking about a specific position at a specific clock reading. So we're going to move that starting position to the other side. We're going to put it way, way, way over here. But it's going to also, we're not going to be looking at changing clock readings anymore. We're going to be looking at a specific clock reading. So the red triangle of this equation is still 1/2 the acceleration times the clock reading squared plus the initial velocity times the clock reading plus the position at time 0. How is this equation different? Well, this equation helps us find an individual position at a specific clock reading. When what is true? When it's accelerating at time 0, when it has a starting velocity and has a starting position that's not 0. If you had a problem that wasn't accelerating, you could actually solve this without the acceleration part. So you would just need the starting velocity and the how long or what time it was and where it was at time 0. All right. Or if the initial position was 0, it would just be the final position is how fast it's going plus whatever clock reading it's at. So you can find a clock reading at any of those spots. So ultimately, this can solve for a position for something that's at rest but is accelerating, but started off at rest, or for an object that is accelerating. Not going to have to back out all of these either. And in this format, it gives us a final position for an object that is accelerating and moving it times 0, and had a starting position that was not 0. So ultimately, we've got 3 big equations that we came up with on here, using adding the area of the blue rectangle plus the red triangle. First, we know that the total displacement is simply the area of the triangle plus the area of the rectangle. Then we found displacement for an object that is accelerating and moving at time 0. Finally, we found the position for an object that is accelerating, it's moving at time 0, and had a starting position that was not 0. I hope that helps. Again, there are notes attached to this if you'd like to read through them on your own. And basically, I'm not going to ask you to be able to regurgitate this back to me, but we would like you to be able to know where this information come from and know that it came from things that we studied earlier. I hope that helps.